So what do a massive power blackout, the way a virus spreads, and even your own career path have in common? It might sound like a riddle, but the answer is pretty incredible. They're all secretly being run by a hidden architecture of connections. Today, we're going to pull back the curtain on this amazing field called network science and see the invisible links that pretty much shape our entire world. Okay, so here's the game plan. We're going to start with the wild story of a huge blackout, just to see why this stuff is so important. Then, we'll zoom out and see how basically everything, from our own bodies to all of society, is just a bunch of networks. We'll get into the core ideas of this new science, check out some of its incredible real-world applications, and then we'll wrap it all up with the key takeaways so you walk away really getting it. All right, let's kick things off with a problem. A really, really dark problem that tells us something fundamental about the world we live in today. Check this out. On August 14, 2003, this is what the Northeast United States and parts of Canada looked like from space. On the left, you see a normal night, all lit up and buzzing with energy. And on the right, just hours later, in eerie, sweeping darkness. We're talking major cities like Toronto, Detroit, Cleveland, all plunged into darkness. 55 million people just without power. Now, the crazy part is this wasn't some huge disaster or a big coordinated attack. Nope. It all started with something tiny, a small, local problem in Ohio. So that brings us to the big mystery. How on earth does one little hiccup in one place trigger a crisis across a continent?
Well, the answer is a concept with a pretty cool name, a cascading failure. The easiest way to think about it is like a line of dominoes. When one piece of a network goes down, all the load it was carrying, whether that's electricity or, say, financial risk, it has to go somewhere. It gets shoved off onto its neighbors. But what if they can't handle that extra load? Well, then they fail too, and they push an even bigger load onto the next guys in line. And just like that, a tiny local glitch snowballs into a massive, system-wide collapse.
And this gets us right to the heart of something called the interconnectivity paradox. See, there's a really good reason we build these giant connected power grids. It's super efficient, it keeps prices low, and it lets us move power around in an instant. But the very thing that makes the system so efficient is also what makes it so fragile. That deep connection is what lets a tiny problem in one spot have a huge impact hundreds of miles away. Our greatest strength becomes our biggest vulnerability. But this isn't just about power grids. That blackout was really just a symptom of a much, much bigger idea. The truth is, we live in a world that is jam-packed with what scientists call complex systems.
The great Stephen Hawking even predicted it. He said that figuring out complexity was going to be the central challenge of our time. And he was right. From our economies to entire ecosystems, we're surrounded by these massive systems that are just incredibly hard to predict.
So, what the heck is a complex system? Well, it's any system where the whole is way more than just the sum of its parts. Think about it. You can't understand a traffic jam just by studying one car. You can't understand the economy by studying one person. The magic and the real mystery is in how all the pieces interact. And that's exactly what network science does. It gives us the map to see those interactions. And this is where it gets really fun. Once you start looking for them, you see these networks literally everywhere. The miracle of life itself, that's a cellular network of genes and proteins all talking to each other. Your own consciousness, it's born from the neural network inside your brain. Society, the economy, all of our technology, it's all built on top of this hidden layer of connections.
Now you might be thinking, okay, a network of proteins inside a cell can't possibly have anything in common with, like, my friends on Instagram, and for a long, long time, scientists in their different fields all thought the same way. But then, they stumbled onto something that changed everything.
This huge discovery is a concept called universality, and it is a wild idea. It's the notion that even though all these networks look totally different on the surface, the architecture underneath is governed by the same fundamental laws and principles. Seriously. The math that describes how a disease spreads through a population might look shockingly similar to the math that describes how a funny cat video goes viral online. The components are different, but the blueprint is the same.
For example, take a look at this. It's the wiring diagram of a mouse's brain. A biological network, right? Insanely complex, built by millions of years of evolution. Network scientists study the deep principles that give it this structure.
Okay, now look at this. It's a network map used to understand military operations in Afghanistan. It shows everything from troop locations to the local economy to public opinion. It looks like a completely different universe, right? But, and this is the amazing part, the same mathematical tools we use to make sense of the brain can be used on this map to figure out the flow of power and influence. That's universality in action.
And listen, this isn't some weird fringe theory. The idea of universality is so big it's become a major focus for modern science. We're talking special issues of the world's top journals like Science. It's a real paradigm shift in how we solve problems.
So how do people actually do network science? What's the method? Well, let's break down the 4 key things that really define the field. First, it's interdisciplinary. It's basically a common language that lets a biologist, a computer scientist, and a sociologist all work together on the same problem. Second, it's empirical. This isn't just about abstract ideas. It's driven by real-world data. Third, it's quantitative. It uses some serious math to find patterns you'd never see with your naked eye. And finally, it's computational. You need serious computing power to map and analyze networks that can have millions or even billions of connections.
Okay, the theory is cool, but what's the actual payoff here? How does knowing about these networks actually help us in the real world? Well, let's look at a few game-changing examples.
This right here shows the predicted spread of the H1N1 pandemic from 2009. And this was a huge deal because, for the first time in human history, scientists could accurately forecast in real time how a global pandemic would spread. How'd they do it? By mapping the global transportation network, all the flights, connecting all the cities, and treating it like a network for the virus to travel on. This lets us get ahead of an outbreak, sending medicine and resources where they're going to be needed next.
It's also transforming the business world. Companies can now map their informal networks, not the official org chart, but who really talks to who to get advice and get work done. And the results are often shocking. They find that the true influencer, the person who's a critical hub for information, might not be a manager at all. It could be an engineer in the corner cubicle who just happens to connect everyone.
And then there's medicine, where the impact is just revolutionary. See, for a long time, we tried to cure diseases by fixing one broken part, like a mechanic fixing a single bad spark plug. But new fields like network medicine realize that diseases like cancer aren't just one broken part. They're a breakdown in the communication of the entire system, the entire network. By understanding that network, we can create smarter drugs that help bring the whole system back into balance.
All right, let's bring it all home. If this were a class and you're prepping for the final exam, these are the absolute must-know concepts from our tour of network science.
So first, remember the blackout. That showed us the very real danger of cascading failures, and it introduced us to the interconnectivity paradox, the idea that a network's biggest strength can also be its greatest weakness. Then we hit that mind-bending concept of universality, the discovery that all these different networks actually play by the same basic rules. And finally, we saw the methodology of how it's done. It's a mix of different fields, driven by data, grounded in math, and powered by computers.
You know, from the people you know, to the information you see, to the opportunities you get, your entire life is being shaped by networks you probably never even notice. We just spent the last few minutes making those invisible structures a little more visible. So the only question left is, now that you can see them, what are you going to change?